This book is read by Neil deGrasse Tyson.
For all those who are too busy to read fat books, yet nonetheless seek a conduit to the cosmos. Preface. In recent years, no more than a week goes by without news of a cosmic discovery worthy of banner headlines. While media gatekeepers may have developed an interest in the universe, this rise in coverage likely comes from a genuine increase in the public's appetite for science. Evidence for this abounds, from hit television shows inspired or informed by science, to the success of science fiction films starring marquee actors and brought to the screen by celebrated producers and directors. And lately, theatrical release biopics featuring important scientists have become a genre unto itself. There's also widespread interest around the world in science festivals, science fiction conventions, and science documentaries for television. The highest-grossing film of all time is by a famous director who set a story on a planet orbiting a distant star. And it features a famous actress who plays an astrobiologist. While most branches of science have ascended in this era, the field of astrophysics persistently rises to the top. I think I know why. At one time or another, every one of us has looked up at the night sky and wondered, what does it all mean? How does it all work? And what is my place in the universe? If you're too busy to absorb the cosmos via classes, textbooks, or documentaries, and you nonetheless seek a brief but meaningful introduction to the field, I offer you Astrophysics for People in a Hurry. In this slim volume, you will earn a foundational fluency in all the major ideas and discoveries that drive our modern understanding of the universe. If I've succeeded, you'll be culturally conversant in my field of expertise, and you just may be hungry for more. The universe is under no obligation to make sense to you. Chapter 1. The greatest story ever told. The world has persisted many a long year, having once been set going into the appropriate motions. From these, everything else follows. Lucretius, 50 BC. In the beginning, nearly 14 billion years ago, all the space and all the matter and all the energy of the known universe was contained in a volume less than 1/trillionth the size of the period that ends this sentence. Conditions were so hot, the basic forces of nature that collectively described the universe were unified. Though still unknown how it came into existence, this sub-pinpoint-sized cosmos could only expand rapidly in what today we call the Big Bang. Einstein's general theory of relativity, put forth in 1916, gives us our modern understanding of gravity, in which the presence of matter and energy curves the fabric of space and time surrounding it. In the 1920s, quantum mechanics would be discovered, providing our modern account of all that is small: molecules, atoms, and subatomic particles. But these two understandings of nature are formally incompatible with one another, which set physicists off on a race to blend the theory of the small with the theory of the large into a single coherent theory of quantum gravity. Although we haven't yet reached the finish line, we know exactly where the high hurdles are. One of them is during the Planck era of the early universe. That's the interval of time from t equals 0 up to t equals 10 to the minus 43 seconds. 1/10 million trillion trillion trillionths of a second after the beginning. And before the universe grew to 10 to the minus 35 meters, 100 billion trillion trillionths of a meter across. The German physicist Max Planck, after whom these unimaginably small quantities are named, introduced the idea of quantized energy in 1900 and is generally credited as the father of quantum mechanics. The clash between gravity and quantum mechanics poses no practical problem for the contemporary universe. Astrophysicists apply the tenets and tools of general relativity and quantum mechanics to very different classes of problems. But in the beginning, during the Planck era, the large was small, and we suspect there must have been a kind of shotgun wedding between the two. Alas, the vows exchanged during that ceremony continue to elude us, and so no known laws of physics describe with any confidence the behavior of the universe over that time. We nonetheless expect that by the end of the Planck era, gravity wriggled loose from the other still unified forces of nature, achieving an independent identity nicely described by our current theories. As the universe aged through 10 to the minus 35 seconds, it continued to expand, diluting all concentrations of energy, and what remained of the unified forces split into the electroweak and the strong nuclear forces. Later still, the electroweak force split into the electromagnetic and the weak nuclear forces, laying bare the four distinct forces we have come to know and love, with the weak force controlling radioactive decay, the strong force binding the atomic nucleus, the electromagnetic force binding molecules, and gravity binding bulk matter. A trillionth of a second has passed since the beginning. All the while, the interplay of matter in the form of subatomic particles and energy in the form of photons, massless vessels of light energy that are as much waves as they are particles, was incessant. The universe was hot enough for these photons to spontaneously convert their energy into matter-antimatter particle pairs, which immediately thereafter annihilate, returning their energy back to photons. Yes, antimatter is real, and we discovered it, not science fiction writers. These transmogrifications are entirely prescribed by Einstein's most famous equation, E equals mc squared, which is a two-way recipe for how much matter your energy is worth and how much energy your matter is worth. The c squared is the speed of light squared, a huge number which, when multiplied by the mass, reminds us how much energy you actually get in this exercise. Shortly before, during, and after the strong and electroweak forces parted company, the universe was a seething soup of quarks, leptons, and their antimatter siblings, along with bosons, the particles that enable their interactions. None of these particle families is thought to be divisible into anything smaller or more basic, though each comes in several varieties. The ordinary photon is a member of the boson family. The leptons most familiar to the non-physicist are the electron and perhaps the neutrino. And the most familiar quarks are, well, there are no familiar quarks. Each of their 6 subspecies has been assigned an abstract name that serves no real philological, philosophical, or pedagogical purpose, except to distinguish it from others. Up and down, strange and charmed, and top and bottom. Bosons, by the way, are named for the Indian scientist Satyendra Nath Bose. The word lepton derives from the Greek leptos, meaning light or small. Quark, however, has a literary and far more imaginative origin. The physicist Murray Gell-Mann, who in 1964 proposed the existence of quarks as the internal constituents of neutrons and protons, and who, at the time, thought the quark family had only 3 members, drew the name from a characteristically elusive line in James Joyce's Finnegan's Wake. 3 quarks for Muster Mark. One thing quarks do have going for them: all their names are simple. Something chemists, biologists, and especially geologists seem incapable of achieving when naming their own stuff. Quarks are quirky beasts. Unlike protons, each with an electric charge of +1, and electrons with a charge of -1, quarks have fractional charges that come in thirds. And you'll never catch a quark all by itself. It will always be clutching other quarks nearby. In fact, the force that keeps 2 or more of them together actually grows stronger the more you separate them, as if they were attached by some sort of subnuclear rubber band. Separate the quarks enough, the rubber band snaps, and the stored energy summons E equals mc squared to create a new quark at each end, leaving you back where you started. During the quark-lepton era, the universe was dense enough for the average separation between unattached quarks to rival the separation between attached quarks. Under those conditions, allegiance between adjacent quarks could not be unambiguously established, and they moved freely among themselves, in spite of being collectively bound to one another. The discovery of this state of matter, a kind of quark cauldron, was reported for the first time in 2002, by a team of physicists at the Brookhaven National Laboratories, Long Island, New York. Strong theoretical evidence suggests that an episode in the very early universe, perhaps during one of the force splits, endowed the universe with a remarkable asymmetry, in which particles of matter barely outnumbered particles of antimatter, by about 1,000,000,001 to 1,000,000,000. That small difference in population would hardly get noticed by anybody amid the continuous creation, annihilation, and recreation of quarks and antiquarks, electrons and anti-electrons, better known as positrons, and neutrinos and antineutrinos. The odd man out had oodles of opportunity to find somebody to annihilate with, and so did everybody else. But not for much longer. As the cosmos continued to expand and cool, growing larger than the size of our solar system, the temperature dropped rapidly, below 1,000,000,000,000 degrees Kelvin. A millionth of a second has passed since the beginning. This tepid universe was no longer hot enough or dense enough to cook quarks, and so they all grabbed dance partners, creating a permanent new family of heavy particles called hadrons, from the Greek hadros, meaning thick. That quark to hadron transition soon resulted in the emergence of protons and neutrons, as well as other less familiar heavy particles, all composed of various combinations of quark species. In Switzerland, back on Earth, the European Particle Physics Collaboration, CERN, uses a large accelerator to collide beams of hadrons in an attempt to recreate these very conditions. This largest machine in the world is sensibly called the Large Hadron Collider. The slight matter-antimatter asymmetry afflicting the quark-lepton soup now passed to the hadrons, but with extraordinary consequences. As the universe continued to cool, the amount of energy available for the spontaneous creation of basic particles dropped. During the hadron era, ambient photons could no longer invoke E equals mc squared to manufacture quark-antiquark pairs. Not only that, the photons that emerged from all the remaining annihilations lost energy to the ever-expanding universe, dropping below the threshold required to create hadron-antihadron pairs. For every 1,000,000,000 annihilations, leaving 1,000,000,000 photons in their wake, a single hadron survived. Those loners would get to have all the fun, serving as the ultimate source of matter to create galaxies, stars, planets, and petunias. Without the 1,000,001 to 1,000,000,000 imbalance between matter and antimatter, all mass in the universe would have self-annihilated, leaving a cosmos made of photons and nothing else. The ultimate let there be light scenario. By now, 1 second of time has passed. The universe has grown to a few light years across, about the distance from the sun to its closest neighboring stars. At 1,000,000,000 degrees, it's still plenty hot and still able to cook electrons, which, along with their positron counterparts, continue to pop in and out of existence. But in the ever-expanding, ever-cooling universe, their days, seconds really, are numbered. What was true for quarks and true for hadrons had become true for electrons. Eventually, only one electron in 1,000,000,000 survives. The rest annihilate with positrons, their antimatter sidekicks, in a sea of photons. Right about now, one electron for every proton has been frozen into existence. As the cosmos continues to cool, dropping below 100,000,000 degrees, protons fuse with other protons as well as with neutrons, forming atomic nuclei, and hatching a universe in which 90% of these nuclei are hydrogen and 10% are helium, along with trace amounts of deuterium, heavy hydrogen, tritium, even heavier hydrogen, and lithium. 2 minutes have now passed since the beginning. For another 380,000 years, not much will happen to our particle soup. Throughout these millennia, the temperature remains hot enough for electrons to roam free among the photons, batting them to and fro as they interact with one another. But this freedom comes to an abrupt end when the temperature of the universe falls below 3,000 degrees Kelvin, about half the temperature of the sun's surface, and all the free electrons combine with nuclei. The marriage leaves behind a ubiquitous bath of visible light, forever imprinting the sky with a record of where all the matter was in that moment, and completing the formation of particles and atoms in the primordial universe. For the first billion years, the universe continued to expand and cool as matter gravitated into the massive concentrations we call galaxies. Nearly 100 billion of them formed, each containing hundreds of billions of stars that undergo thermonuclear fusion in their cores. Those stars, with more than about 10 times the mass of the Sun, achieve sufficient pressure and temperature in their cores to manufacture dozens of elements heavier than hydrogen, including those that compose planets and whatever life may thrive upon them. These elements would be stunningly useless were they to remain where they formed, but high-mass stars fortuitously explode, scattering their chemically enriched guts throughout the galaxy. After 9 billion years of such enrichment in an undistinguished part of the universe, the outskirts of the Virgo supercluster, in an undistinguished galaxy, the Milky Way, in an undistinguished region, the Orion Arm, an undistinguished star, the Sun, was born. The gas cloud from which the Sun formed contained a sufficient supply of heavy elements to coalesce and spawn a complex inventory of orbiting objects that includes several rocky and gaseous planets, hundreds of thousands of asteroids, and billions of comets. For the first several 100 million years, large quantities of leftover debris in wayward orbits would accrete onto larger bodies. This occurred in the form of high-speed, high-energy impacts, which rendered molten the surfaces of the rocky planets, preventing the formation of complex molecules. As less and less accretable matter remained in the solar system, planet surfaces began to cool. The one we call Earth formed in a kind of Goldilocks zone around the Sun, where oceans remain largely in liquid form. Had Earth been much closer to the Sun, the oceans would have evaporated. Had Earth been much farther away, the oceans would have frozen. In either case, life as we know it would not have evolved. Within the chemically rich liquid oceans, by a mechanism yet to be discovered, organic molecules transition to self-replicating life. Dominant in this primordial soup were simple anaerobic bacteria, life that thrives in oxygen-empty environments, but excretes chemically potent oxygen as one of its byproducts. These early single-celled organisms unwittingly transformed Earth's carbon dioxide-rich atmosphere into one with sufficient oxygen to allow aerobic organisms to emerge and dominate the oceans and land. These same oxygen atoms, normally found in pairs, O2, also combined in threes to form ozone, O3, in the upper atmosphere, which serves as a shield that protects Earth's surface from most of the Sun's molecule-hostile ultraviolet photons. We owe the remarkable diversity of life on Earth, and we presume elsewhere in the universe, to the cosmic abundance of carbon and the countless number of simple and complex molecules that contain it. There is no doubt about it. More varieties of carbon-based molecules exist than all other kinds of molecules combined. But life is fragile. Earth's occasional encounters with large, wayward comets and asteroids, a formerly common event, wreaks intermittent havoc upon our ecosystem. A mere 65 million years ago, less than 2% of Earth's past, a 10 trillion-ton asteroid hit what is now the Yucatan Peninsula and obliterated more than 70% of Earth's flora and fauna, including all the famous outsized dinosaurs. Extinction. This ecological catastrophe enabled our mammal ancestors to fill freshly vacant niches rather than continue to serve as hors d'oeuvres for T-Rex. One big-brained branch of these mammals, that which we call primates, evolved a genus and species, Homo sapiens, with sufficient intelligence to invent methods and tools of science, and to deduce the origin and evolution of the universe. What happened before all this? What happened before the beginning? Astrophysicists have no idea, or rather, our most creative ideas have little or no grounding in experimental science. In response, some religious people assert, with a tinge of righteousness, that something must have started it all, a force greater than all others, a source from which everything issues, a prime mover. In the mind of such a person, that something is, of course, God. But what if the universe was always there, in a state or condition we have yet to identify? A multiverse, for instance, that continually births universes. Or what if the universe just popped into existence from nothing? Or what if everything we know and love were just a computer simulation rendered for entertainment by a superintelligent alien species? These philosophically fun ideas usually satisfy nobody. Nonetheless, they remind us that ignorance is the natural state of mind for a research scientist. People who believe they are ignorant of nothing have neither looked for nor stumbled upon the boundary between what is known and unknown in the universe. What we do know, and what we can assert without further hesitation, is that the universe had a beginning. The universe continues to evolve. And yes, every one of our body's atoms is traceable to the Big Bang and to the thermonuclear furnaces within high-mass stars that exploded more than 5 billion years ago. We are stardust brought to life, then empowered by the universe to figure itself out. And we have only just begun. Chapter 2. On Earth as in the Heavens. Until Sir Isaac Newton wrote down the universal law of gravitation, nobody had any reason to presume that the laws of physics at home were the same everywhere else in the universe. Earth had earthly things going on, and heavens had heavenly things going on. According to Christian teachings of the day, God controlled the heavens, rendering them unknowable to our feeble mortal minds. When Newton breached this philosophical barrier by rendering all motion comprehensible and predictable, some theologians criticized him for leaving nothing for the Creator to do. Newton had figured out that the force of gravity pulling ripe apples from their orchards also guides tossed objects along their curved trajectories and directs the moon in its orbit around Earth. Newton's law of gravity also guides planets, asteroids, and comets in their orbits around the sun, and keeps hundreds of billions of stars in orbit within our Milky Way galaxy. This universality of physical laws drives scientific discovery like nothing else. And gravity was just the beginning. Imagine the excitement among 19th century astronomers when laboratory prisms, which break light beams into a spectrum of colors, were first turned to the sun. Spectra are not only beautiful, but contain oodles of information about the light-emitting object, including its temperature and composition. Chemical elements reveal themselves by their unique patterns of light or dark bands that cut across the spectrum. To people's delight and amazement, the chemical signatures on the sun were identical to those in the laboratory. No longer the exclusive tool of chemists, the prism showed that as different as the sun is from Earth in size, mass, temperature, location, and appearance, we both contain the same stuff: hydrogen, carbon, oxygen, nitrogen, calcium, iron, and so forth. But more important than our laundry list of shared ingredients was the recognition that the laws of physics prescribing the formation of these spectral signatures on the sun were the same laws operating on Earth, 93 million miles away. So fertile was this concept of universality that it was successfully applied in reverse. Further analysis of the sun's spectrum revealed the signature of an element that had no known counterpart on Earth. Being of the sun, the new substance was given a name derived from the Greek word helios, the sun, and was only later discovered in the lab. Thus, helium became the first and only element in the chemist's periodic table to be discovered someplace other than Earth. Okay, the laws of physics work in the solar system, but do they work across the galaxy, across the universe, across time itself? Step by step, the laws were tested. Nearby stars also revealed familiar chemicals. Distant binary stars, bound in mutual orbit, seem to know all about Newton's laws of gravity. For the same reason, so do binary galaxies. And like the geologist's stratified sediments, which serve as a timeline of earthly events, the farther away we look in space, the further back in time we see. Spectra from the most distant objects in the universe show the same chemical signatures that we see nearby in space and in time. True, heavy elements were less abundant back then. They are manufactured primarily in subsequent generations of exploding stars. But the laws describing the atomic and molecular processes that created these spectral signatures remain intact. In particular, a quantity known as the fine structure constant, which controls the basic fingerprinting for every element, must have remained unchanged for billions of years. Of course, not all things and phenomena in the cosmos have counterparts on Earth. You've probably never walked through a cloud of glowing million-degree plasma, and I bet you've never greeted a black hole on the street. What matters is the universality of the physical laws that describe them. When spectral analysis was first applied to the light emitted by interstellar nebulae, a signature was discovered that, once again, had no counterpart on Earth. At the time, the periodic table of elements had no obvious place for a new element to fit. In response, astrophysicists invented the name nebulium as a placeholder until they could figure out what was going on. Turned out that in space, gaseous nebulae are so rarefied that atoms go long stretches without colliding. Under these conditions, electrons can do things within atoms that had never before been seen in Earth labs. Nebulium was simply the signature of ordinary oxygen doing extraordinary things. This universality of physical laws tells us that if we land on another planet with a thriving alien civilization, they will be running on the same laws that we have discovered and tested here on Earth, even if the aliens harbor different social and political beliefs. Furthermore, if you want to talk to the aliens, you can bet they don't speak English or French or even Mandarin. Nor would you know whether shaking their hands, if indeed their outstretched appendage is a hand, would be considered an act of war or peace. Your best hope is to find a way to communicate using the language of science. Such an attempt was made in the 1970s with Pioneer 10 and 11 and Voyager 1 and 2. All 4 spacecraft were endowed with enough energy after gravity assist from the giant planets to escape the solar system entirely. Pioneer wore a golden etched plaque that showed in scientific pictograms the layout of our solar system, our location in the Milky Way galaxy, and the structure of the hydrogen atom. Voyager went further and also included a gold record album containing diverse sounds from Mother Earth, including the human heartbeat, whale songs, and musical selections from around the world, including the works of Beethoven and Chuck Berry. While this humanized the message, it's not clear whether alien ears would have a clue what they were listening to, assuming they have ears in the first place. My favorite parody of this gesture was a skit on NBC's Saturday Night Live, shortly after the Voyager launch, in which they showed a written reply from the aliens who recovered the spacecraft. The note simply requested, "Send more Chuck Berry." Science thrives not only on the universality of physical laws, but also on the existence and persistence of physical constants. The constant of gravitation, known by most scientists as Big G, supplies Newton's equation of gravity with the measure of how strong the force will be. This quantity has been implicitly tested for variation over eons. If you do the math, you can determine that a star's luminosity is steeply dependent on Big G. In other words, if Big G had been even slightly different in the past, then the energy output of the sun would have been far more variable than anything the biological, climatological, or geological records indicate. Such is the uniformity of our universe. Among all constants, the speed of light is the most famous. No matter how fast you go, you will never overtake a beam of light. Why not? No experiment ever conducted has ever revealed an object of any form reaching the speed of light. Well-tested laws of physics predict and account for that fact. I know these statements sound close-minded. Some of the most boneheaded science-based proclamations in the past have underestimated the ingenuity of inventors and engineers. We will never fly. Flying will never be commercially feasible. We will never split the atom. We will never break the sound barrier. We will never go to the moon. What they have in common is that no established law of physics stood in their way. The claim we will never outrun a beam of light is a qualitatively different prediction. It flows from basic time-tested physical principles. Highway signs for interstellar travelers of the future will justifiably read, "The speed of light." It's not just a good idea, it's the law. Unlike getting caught speeding on Earth roads, the good thing about the laws of physics is that they require no law enforcement agencies to maintain them. Although, I did once own a geeky t-shirt that proclaimed, "Obey gravity." All measurements suggest that the known fundamental constants and the physical laws that reference them are neither time-dependent nor location-dependent. They're truly constant and universal. Many natural phenomena manifest multiple physical laws operating at once. This fact often complicates the analysis, and in most cases requires high-performance computing to calculate what's going on and to keep track of important parameters. When comet Shoemaker-Levy 9 plunged into Jupiter's gas-rich atmosphere in July 1994 and then exploded, the most accurate computer model combined the laws of fluid mechanics, thermodynamics, kinematics, and gravitation. Climate and weather represent other leading examples of complicated and difficult to predict phenomena, but the basic laws governing them are still at work. Jupiter's Great Red Spot, a raging anticyclone that's been going strong for at least 350 years, is driven by identical physical processes that generate storms on Earth and elsewhere in the solar system. Another class of universal truths is the conservation laws, where the amount of some measured quantity remains unchanged no matter what. The three most important are the conservation of mass and energy, conservation of linear and angular momentum, and the conservation of electric charge. These laws are in evidence on Earth and everywhere we have thought to look, from the domain of particle physics to the large-scale structure of the universe. In spite of this boasting, all is not perfect in paradise. It happens that we cannot see, touch, or taste the source of 85% of the gravity we measure in the universe. This mysterious dark matter, which remains undetected except for its gravitational pull on matter we see, may be composed of exotic particles that we have yet to discover or identify. A small minority of astrophysicists, however, are unconvinced and have suggested that there is no dark matter. You just need to modify Newton's law of gravity. Simply add a few components to the equations, and all will be well. Perhaps one day we will learn that Newton's gravity indeed requires adjustment. That'll be okay. It has happened once before. Einstein's 1916 general theory of relativity expanded on the principles of Newton's gravity in a way that also applied to objects of extremely high mass. Newton's law of gravity breaks down in this expanded realm, which was unknown to him. The lesson here is that our confidence flows through the range of conditions over which a law has been tested and verified. The broader that range, the more potent and powerful the law becomes in describing the cosmos. For ordinary household gravity, Newton's law works just fine. It got us to the moon and returned us safely to Earth in 1969. For black holes in the large-scale structure of the universe, we need general relativity. And if you insert low mass and low speeds into Einstein's equations, they literally, or rather mathematically, become Newton's equations. All good reasons to develop confidence in our understanding and of all we claim to understand. To the scientist, the universality of physical laws makes the cosmos a marvelously simple place. By comparison, human nature, the psychologist's domain, is infinitely more daunting. In America, local school boards vote on subjects to be taught in the classroom. In some cases, votes are cast according to the whims of cultural, political, or religious tides. Around the world, varying belief systems lead to political differences that are not always resolved peacefully. The power and beauty of physical laws is that they apply everywhere, whether or not you choose to believe in them. In other words, after the laws of physics, everything else is opinion. Not that scientists don't argue, we do, a lot. But when we do, we typically express opinions about the interpretation of insufficient or ratty data on the bleeding frontier of our knowledge. Wherever and whenever a physical law can be invoked in the discussion, the debate is guaranteed to be brief. No, your idea for a perpetual motion machine will never work. It violates well-tested laws of thermodynamics. No, you can't build a time machine that will enable you to go back and kill your mother before you were born. It violates causality laws. And without violating momentum laws, you cannot spontaneously levitate and hover above the ground, whether or not you are seated in the lotus position. You could, in principle, perform this stunt if you managed to let forth a powerful and sustained exhaust of flatulence. Knowledge of physical laws can, in some cases, give you the confidence to confront surly people. A few years ago, I was having a hot cocoa nightcap at a dessert shop in Pasadena, California. Ordered it with whipped cream, of course. When it arrived at the table, I saw no trace of this. After I told the waiter that my cocoa had no whipped cream, he asserted I couldn't see it because it sank to the bottom. But whipped cream has low density and floats on all liquids that humans consume. So I offered the waiter two possible explanations. Either somebody forgot to add the whipped cream to my hot cocoa, or the universal laws of physics were different in his restaurant. Unconvinced, he defiantly brought over a dollop of whipped cream to demonstrate his claim. After bobbing once or twice, the whipped cream rose to the top, safely afloat. What better proof do you need of the universality of physical law? Chapter 3. Let There Be Light. After the Big Bang, the main agenda of the cosmos was expansion, ever diluting the concentration of energy that filled space. With each passing moment, the universe got a little bit bigger, a little bit cooler, and a little bit dimmer. Meanwhile, matter and energy co-inhabited a kind of opaque soup in which free-range electrons continually scattered photons every which way. For 380,000 years, things carried on that way. In this early epoch, photons didn't travel far before encountering an electron. Back then, if your mission had been to see across the universe, you could. Any photon you detected had careened off an electron right in front of your nose, nano and picoseconds earlier, a billionth and a trillionth of a second. Since that's the largest distance that information can travel before reaching your eyes, the entire universe was simply a glowing, opaque fog in every direction you looked. The sun and all other stars behaved this way too. As the temperature drops, particles move more and more slowly, and so right about then, when the temperature of the universe first dipped below a red-hot 3,000 degrees Kelvin, electrons slowed down just enough to be captured by passing photons, thus bringing full-fledged atoms into the world. This allowed previously harassed photons to be set free and travel on uninterrupted paths across the universe. This cosmic background is the incarnation of the leftover light from a dazzling, sizzling early universe, and can be assigned a temperature based on what part of the spectrum the dominant photons represent. As the cosmos continued to cool, the photons that had been born in the visible part of the spectrum lost energy to the expanding universe and eventually slid down the spectrum, morphing into infrared photons. Although the visible light photons had become weaker and weaker, they never stopped being photons. What's next on the spectrum? Today, the universe has expanded by a factor of 1,000 from the time photons were set free. And so, the cosmic background has in turn cooled by a factor of 1,000. All the visible light photons from that epoch have become 1/1000th as energetic. They're now microwaves, which is where we derive the modern moniker Cosmic Microwave Background, or CMB for short. Keep this up, and 50 billion years from now, astrophysicists will be writing about the cosmic radio wave background. When something glows from being heated, it emits light in all parts of the spectrum, but will always peak somewhere. For household lamps that still use glowing metal filaments, the bulbs all peak in the infrared, which is the single greatest contributor to their inefficiency as a source of visible light. Our senses detect infrared only in the form of warmth on our skin. The LED revolution in advanced lighting technology creates pure visible light without wasting wattage on invisible parts of the spectrum. That's how you can get crazy-sounding sentences on packaging, like, 7 watts LED replaces 60 watts incandescent. Being the remnant of something that was once brilliantly aglow, the CMB has the profile we expect of a radiant but cooling object. It peaks in one part of the spectrum, but radiates in other parts of the spectrum as well. In this case, besides peaking in microwaves, the CMB also gives off some radio waves and a vanishingly small number of photons of higher energy. In the mid-20th century, the subfield of cosmology, not to be confused with cosmetology, didn't have much data, and where data are sparse, competing ideas abound that are clever and wishful. The existence of the CMB was predicted by the Russian-born American physicist George Gamow and colleagues during the 1940s. The foundation of these ideas came from the 1927 work of the Belgian physicist and priest Georges Lemaitre, who is generally recognized as the father of Big Bang cosmology. But it was American physicists Ralph Alpher and Robert Herman who in 1948 first estimated what the temperature of the cosmic background ought to be. They based their calculations on 3 pillars. 1. Einstein's 1916 general theory of relativity. 2. Edwin Hubble's 1929 discovery that the universe is expanding. And 3. Atomic physics developed in laboratories before and during the Manhattan Project that built the atomic bombs of World War II. Herman and Alford calculated and proposed a temperature of 5 degrees Kelvin for the universe. Well, that's just plain wrong. The precisely measured temperature of these microwaves is 2.725 degrees, sometimes written as simply 2.7 degrees. And if you're numerically lazy, nobody will fault you for rounding the temperature of the universe to 3 degrees. Let's pause for a moment. Herman and Alford used atomic physics, freshly gleaned in a lab, and applied it to hypothesized conditions in the early universe. From this, they extrapolated billions of years forward, calculating what temperature the universe should be today. That their prediction even remotely approximated the right answer is a stunning triumph of human insight. They could have been off by a factor of 10 or 100, or they could have predicted something that isn't even there. Commenting on this feat, the American astrophysicist J. Richard Gott noted, predicting that the background existed and then getting its temperature correct to within a factor of 2 was like predicting that a flying saucer 50 feet wide would land on the White House lawn, but instead, a flying saucer 27 feet wide actually showed up. The first direct observation of the cosmic microwave background was made inadvertently in 1964 by American physicists Arno Penzias and Robert Wilson at Bell Telephone Laboratories, the research branch of AT&T. In the 1960s, everyone knew about microwaves, but almost no one had the technology to detect them. Bell Labs, a pioneer in the communications industry, developed a beefy horn-shaped antenna for just that purpose. But first, if you're going to send or receive a signal, you don't want too many sources contaminating it. Penzias and Wilson sought to measure background microwave interference to their receiver to enable clean, noise-free communication within this band of the spectrum. They were not cosmologists. They were techno-wizards honing a microwave receiver and unaware of the gamma of Herman and Alford predictions. What Penzias and Wilson were decidedly not looking for was the cosmic microwave background. They were just trying to open a new channel of communication for AT&T. Penzias and Wilson ran their experiment and subtracted from their data all the known terrestrial and cosmic sources of interference they could identify. But one part of the signal didn't go away, and they just couldn't figure out how to eliminate it. Finally, they looked inside the dish and saw pigeons nesting there. They were worried that a white dielectric substance, pigeon poop, might be responsible for the signal, because they detected it no matter what direction the detector pointed. After cleaning out the dielectric substance, the interference dropped a little bit, but a leftover signal remained. The paper they published in 1965 was all about this unaccountable excess antenna temperature. Meanwhile, a team of physicists at Princeton, led by Robert Dicke, was building a detector specifically to find the CMB. But they didn't have the resources of Bell Labs, so their work went a little slower. And the moment Dicke and his colleagues heard about Penzias and Wilson's work, the Princeton team knew exactly what the observed excess antenna temperature was. everything fit, especially the temperature itself, and that the signal came from every direction in the sky. In 1978, Penzias and Wilson won the Nobel Prize for their discovery. And in 2006, American astrophysicists John C. Mather and George F. Smoot would share the Nobel Prize for observing the CMB over a broad range of the spectrum, bringing cosmology from a nursery of clever but untested ideas into the realm of a precision experimental science. Because light takes time to reach us from distant places in the universe, if we look out in deep space, we actually see eons back in time. So if the intelligent inhabitants of a galaxy far, far away were to measure the temperature of the cosmic background radiation at the moment captured by our gaze, they should get a reading higher than 2.7 degrees, because they are living in a younger, smaller, hotter universe than we are. Turns out you can actually test this hypothesis. The molecule cyanogen, CN, once used on convicted murderers as the active component of the gas administered by their executioners, gets excited by exposure to microwaves. If the microwaves are warmer than the ones in our CMB, they excite the molecule a little more. In the Big Bang model, the cyanogen in distant younger galaxies gets bathed in a warmer cosmic background than the cyanogen in our own Milky Way galaxy. And that's exactly what we observe. You can't make this stuff up. Why should any of this be interesting? The universe was opaque until 380,000 years after the Big Bang, so you could not have witnessed matter taking shape, even if you'd been sitting front row center. You couldn't have seen where the galaxy clusters and voids were starting to form. Before anybody could have seen anything worth seeing, photons had to travel unimpeded across the universe as carriers of this information. The spot where each photon began its cross-cosmos journey is where it had smacked into the last electron that would ever stand in its way, the point of last scatter. As more and more photons escape unsmacked, they create an expanding surface of last scatter, some 120,000 years deep. That surface is where all the atoms in the universe were born. An electron joins an atomic nucleus, and a little pulse of energy in the form of a photon soars away into the wild red yonder. By then, some regions of the universe have already begun to coalesce by the gravitational attraction of their parts. Photons that last scattered off electrons in these regions developed a different, slightly cooler profile than those scattering off the less sociable electrons sitting in the middle of nowhere. Where matter accumulated, the strength of gravity grew, enabling more and more matter to gather. These regions seeded the formation of galaxy superclusters, while other regions were left relatively empty. When you map the cosmic microwave background in detail, you find that it's not completely smooth. It's got spots that are slightly hotter and slightly cooler than average. By studying these temperature variations in the CMB, that is to say, by studying patterns in the surface of last scatter, we can infer what the structure and content of the matter was in the early universe. To figure out how galaxies and clusters and superclusters arose, we use our best probe, the CMB, a potent time capsule that empowers astrophysicists to reconstruct cosmic history in reverse. Studying its patterns is like performing some sort of cosmic phrenology as we analyze the skull bumps of the infant universe. When constrained by other observations of the contemporary and distant universe, the CMB enables you to decode all sorts of fundamental cosmic properties. Compare the distribution of sizes and temperatures of the warm and cool areas, and you can infer how strong the force of gravity was at the time, and how quickly matter accumulated, allowing you to then deduce how much ordinary matter, dark matter, and dark energy there is in the universe. From here, it's then straightforward to tell whether or not the universe will expand forever. Ordinary matter is what we're all made of. It has gravity and interacts with light. Dark matter is a mysterious substance that has gravity but does not interact with light in any known way. Dark energy is a mysterious pressure in the vacuum of space that acts in the opposite direction of gravity, forcing the universe to expand faster than it otherwise would. What our phrenological exam says is that we understand how the universe behaved, but that most of the universe is made of stuff about which we are clueless. Our profound areas of ignorance notwithstanding, today as never before, cosmology has an anchor because the CMB reveals the portal through which we all walked. It's a point where interesting physics happened and where we learned about the universe before and after its light was set free. The simple discovery of the cosmic microwave background turned cosmology into something more than mythology. But it was the accurate and detailed map of the cosmic microwave background that turned cosmology into a modern science. Cosmologists have plenty of ego. How could you not when your job is to deduce what brought the universe into existence? Without data, their explanations were just hypotheses. Now, each new observation, each morsel of data, wields a two-edged sword. It enables cosmology to thrive on the kind of foundation so much of the rest of science enjoys. But it also constrains theories that people thought up when there wasn't enough data to say whether they were right or wrong. No science achieves maturity without it. Chapter 4. Between the Galaxies. In the grand tally of cosmic constituents, galaxies are what typically get counted. Latest estimates show that the observable universe may contain 100 billion of them. Bright and beautiful and packed with stars, galaxies decorate the dark voids of space like cities across a country at night. But just how voidy is the void of space? How empty is the countryside between cities? Just because galaxies are in your face, and just because they would have us believe that nothing else matters, the universe may nonetheless contain hard-to-detect things between the galaxies. Maybe those things are more interesting or more important to the evolution of the universe than the galaxies themselves. Our own spiral-shaped galaxy, the Milky Way, is named for its spilled milk appearance to the unaided eye across Earth's nighttime sky. Indeed, the very word galaxy derives from the Greek galaxies, milky. Our pair of nearest neighbor galaxies, 600,000 light-years distant, are both small and irregularly shaped. Ferdinand Magellan's ship's log identified these cosmic objects during his famous round-the-world voyage of 1519. In his honor, we call them the Large and Small Magellanic Clouds, and they're visible primarily from the southern hemisphere as a pair of cloud-like splotches in the sky, parked beyond the stars. The nearest galaxy, larger than our own, is 2 million light-years away beyond the stars that trace the constellation Andromeda. This spiral galaxy, historically dubbed the Great Nebula in Andromeda, is a somewhat more massive and luminous twin of the Milky Way. Notice that the name for each system lacks reference to the existence of stars. Milky Way, Magellanic Cloud, Andromeda Nebula. All three were named before telescopes were invented, so they could not yet be resolved into their stellar constituencies. As detailed in Chapter 9, without the benefit of telescopes operating in multiple bands of light, we might still declare the space between the galaxies to be empty. Aided by modern detectors and modern theories, we have probed our cosmic countryside and revealed all manner of hard-to-detect things. Dwarf galaxies, runaway stars that explode, million-degree X-ray emitting gas, dark matter, faint blue galaxies, ubiquitous gas clouds, super-duper high-energy charged particles, and the mysterious quantum vacuum energy. With a list like that, one could argue that all the fun in the universe happens between the galaxies rather than within them. In any reliably surveyed volume of space, dwarf galaxies outnumber large galaxies by more than 10 to 1. The first essay I ever wrote on the universe in the early 1980s was titled The Galaxy and the Seven Dwarfs, referring to the Milky Way's diminutive nearby family. Since then, the tally of local dwarf galaxies has been counted in the dozens. While full-blooded galaxies contain hundreds of billions of stars, dwarf galaxies can have as few as 1 million, which renders them 100,000 times harder to detect. No wonder they're still being discovered in front of our noses. Images of dwarf galaxies that no longer manufacture stars tend to look like tiny, boring smudges. Those dwarfs that do form stars are all irregularly shaped and, quite frankly, are a sorry-looking lot. Dwarf galaxies have three things working against their detection. They're small, and so they're easily passed over when seductive spiral galaxies vie for your attention. They're dim, and so are missed in many surveys of galaxies that cut off below a pre-specified brightness level. And they have low density of stars within them, so they offer poor contrast above the glow of surrounding light from Earth's nighttime atmosphere and from other sources. All this is true, but since dwarfs far outnumber normal galaxies, perhaps our definition of what is normal needs revision. You will find most known dwarf galaxies hanging out near bigger galaxies, in orbit around them like satellites. The two Magellanic Clouds are part of the Milky Way's dwarf family. But the lives of satellite galaxies can be quite hazardous. Most computer models of their orbits show a slow decay that ultimately results in the hapless dwarfs getting ripped apart and then eaten by the main galaxy. The Milky Way engaged in at least one act of cannibalism in the last billion years, when it consumed a dwarf galaxy whose flayed remains can be seen as a stream of stars orbiting the galactic center beyond the stars of the constellation Sagittarius. The system is called the Sagittarius Dwarf, but should probably have been named Lunch. In the high-density environment of clusters, two or more large galaxies routinely collide and leave behind a titanic mess, spiral structures warped beyond all recognition. Newly induced bursts of star-forming regions spawn from the violent collisions of gas clouds, and hundreds of millions of stars strewn hither and yon, having freshly escaped the gravity of both galaxies. Some stars reassemble to form blobs that could be called dwarf galaxies. Other stars remain adrift. About 10% of all large galaxies show evidence of a major gravitational encounter with another large galaxy, and that rate may be 5 times higher among galaxies and clusters. With all this mayhem, how much galactic flotsam permeates intergalactic space, especially within clusters? Nobody knows for sure. The measurement is difficult because isolated stars are too dim to detect individually. We must rely on detecting a faint glow produced by the light of all stars combined. In fact, observations of clusters detect just such a glow between the galaxies, suggesting that there may be as many vagabond, homeless stars as there are stars within the galaxies themselves. Adding ammo to the discussion, we have found, without looking for them, more than a dozen supernovas that exploded far away from what we presume to be their host galaxies. In ordinary galaxies, for every star that explodes in this way, 100,000 to 1,000,000 do not. So isolated supernovas may betray entire populations of undetected stars. Supernovas are stars that have blown themselves to smithereens and, in the process, have temporarily, over several weeks, increased their luminosity 1 billion-fold, making them visible across the universe. While a dozen homeless supernovas is a relatively small number, many more may await discovery, since most supernova searches systematically monitor known galaxies and not empty space. There's more to clusters than their constituent galaxies and their wayward stars. Measurements made with X-ray sensitive telescopes reveal a space-filling intra-cluster gas at tens of millions of degrees. The gas is so hot that it glows strongly in the X-ray part of the spectrum. The very movement of gas-rich galaxies through this medium eventually strips them of their own gas, forcing them to forfeit their capacity to make new stars. That could explain it, but when you calculate the total mass present in this heated gas, for most clusters, it exceeds the mass of all galaxies in the cluster by as much as a factor of 10. Worse yet, clusters are overrun by dark matter, which happens to contain up to another factor of 10 times the mass of everything else. In other words, if telescopes observed mass rather than light, then our cherished galaxies and clusters would appear as insignificant blips amid a giant spherical blob of gravitational forces. In the rest of space, outside of clusters, there's a population of galaxies that thrived long ago. As already noted, looking out into the cosmos is analogous to a geologist looking across sedimentary strata, where the history of rock formation is laid out in full view. Cosmic distances are so vast that the travel time for light to reach us can be millions or even billions of years. When the universe was half its current age, a very blue and very faint species of intermediate-sized galaxy thrived. We see them. They hail from a long time ago, representing galaxies far, far away. Their blue comes from the glow of freshly formed, short-lived, high-mass, high-temperature, high-luminosity stars. The galaxies are faint, not only because they are distant, but because the population of luminous stars within them is thin. Like the dinosaurs that came and went, leaving birds as their only modern descendant, the faint blue galaxies no longer exist, but presumably have a counterpart in today's universe. Did all their stars burn out? Have they become invisible corpses strewn throughout the universe? Did they evolve into the familiar dwarf galaxies of today? Or were they all eaten by larger galaxies? We do not know, but their place in the timeline of cosmic history is certain. With all this stuff between the big galaxies, we might expect some of it to obscure our view of what lies beyond. This could be a problem for the most distant objects in the universe, such as quasars. Quasars are superluminous galaxy cores whose light has typically been traveling for billions of years across space before reaching our telescopes. As extremely distant sources of light, they make ideal guinea pigs for the detection of intervening junk. Sure enough, when you separate quasar light into its component colors, revealing a spectrum, it's riddled with the absorbing presence of intervening gas clouds. Every known quasar, no matter where on the sky it's found, shows features from dozens of isolated hydrogen clouds scattered across time and space. This unique class of intergalactic object was first identified in the 1980s and continues to be an active area of astrophysical research. Where do they come from? How much mass do they all contain? Every known quasar reveals these hydrogen features, so we conclude that the hydrogen clouds are everywhere in the universe. And as expected, the farther the quasar, the more clouds are present in the spectrum. Some of the hydrogen clouds, less than 1%, are simply the consequence of our line of sight passing through the gas contained in an ordinary spiral or irregular galaxy. You would, of course, expect at least some quasars to fall behind the light of ordinary galaxies that are too distant to detect. But the rest of the absorbers are unmistakable as a class of cosmic object. Meanwhile, quasar light commonly passes through regions of space that contain monstrous sources of gravity, which wreak havoc on the quasar's image. These are often hard to detect because they may be composed of ordinary matter that is simply too dim and distant, or they may be zones of dark matter, such as what occupies the centers and surrounding regions of galaxy clusters. In either case, where there is mass, there is gravity, and where there is gravity, there is curved space, according to Einstein's general theory of relativity. And where space is curved, it can mimic the curvature of an ordinary glass lens and alter the pathways of light that pass through. Indeed, distant quasars and whole galaxies have been lensed by objects that happen to fall along the line of sight to Earth's telescopes. Depending on the mass of the lens itself and the geometry of the line of sight alignments, the lensing action can magnify, distort, or even split the background source of light into multiple images, just like funhouse mirrors at arcades. One of the most distant known objects in the universe is not a quasar, but an ordinary galaxy whose feeble light has been magnified significantly by the action of an intervening gravitational lens. We may henceforth need to rely upon these intergalactic telescopes to peer where and when ordinary telescopes cannot reach, and thus reveal the future holders of the cosmic distance record. Nobody doesn't like intergalactic space, but it can be hazardous to your health if you choose to go there. Let's ignore the fact that you would freeze to death as your warm body tried to reach equilibrium with the 3-degree temperature of the universe. And let's ignore the fact that your blood cells would burst while you suffocated from the lack of atmospheric pressure. These are ordinary dangers. From the Department of Exotic Happenings, intergalactic space is regularly pierced by super-duper high-energy, fast-moving, charged subatomic particles. We call them cosmic rays. The highest energy particles among them have 100 million times the energy that can be generated in the world's largest particle accelerator. Their origin continues to be a mystery, but most of these charged particles are protons, the nuclei of hydrogen atoms, and are moving at 99.9999999999999% of the speed of light. Remarkably, these single subatomic particles carry enough energy to knock a golf ball from anywhere on a putting green into the cup. Perhaps the most exotic happenings between and among the galaxies in the vacuum of space and time is the seething ocean of virtual particles, undetectable matter and antimatter pairs popping in and out of existence. This peculiar prediction of quantum physics has been dubbed the vacuum energy, which manifests as an outward pressure acting counter to gravity that thrives in the total absence of matter. The accelerating universe, dark energy incarnate, may be driven by the action of this vacuum energy. Yes, intergalactic space is and will forever be where the action is. Chapter 5. Dark Matter. Gravity, the most familiar of nature's forces, offers us simultaneously the best and the least understood phenomena in nature. It took the mind of the millennium's most brilliant and influential person, Isaac Newton, to realize that gravity's mysterious action at a distance arises from the natural effects of every bit of matter, and that the attractive force between any two objects can be described by a simple algebraic equation. It took the mind of the last century's most brilliant and influential person, Albert Einstein, to show that we can more accurately describe gravity's action at a distance as a warp in the fabric of space-time, produced by any combination of matter and energy. Einstein demonstrated that Newton's theory requires some modification to describe gravity accurately, to predict, for example, how much light rays will bend when they pass by a massive object. Although Einstein's equations are fancier than Newton's, they nicely accommodate the matter that we have come to know and love, matter that we can see, touch, feel, smell, and occasionally taste. We don't know who's next in the genius sequence, but we've now been waiting nearly a century for somebody to tell us why the bulk of all the gravitational force that we've measured in the universe, about 85% of it, arises from substances that do not otherwise interact with our matter or energy. Or maybe the excess gravity doesn't come from matter and energy at all, but emanates from some other conceptual thing. In any case, we are essentially clueless. We find ourselves no closer to the answer today than we were when this missing mass problem was first fully analyzed in 1937 by the Swiss-American astrophysicist Fritz Zwicky. He taught at the California Institute of Technology for more than 40 years, combining his far-ranging insights into the cosmos with a colorful means of expression and an impressive ability to antagonize his colleagues. Zwicky studied the movement of individual galaxies within a titanic cluster of them, located far beyond the local stars of the Milky Way, that trace out the constellation Coma Berenices, the hair of Berenice, an Egyptian queen of antiquity. The Coma cluster, as we call it, is an isolated and richly populated ensemble of galaxies about 300 million light-years from Earth. Its 1,000 galaxies orbit the cluster's center, moving in all directions like bees swarming a beehive. Using the motions of a few dozen galaxies as tracers of the gravity field that binds the entire cluster, Zwicky discovered that their average velocity had a shockingly high value. Since larger gravitational forces induce higher velocities in the objects they attract, Zwicky inferred an enormous mass for the Coma cluster. As a reality check on that estimate, you can sum up the masses of each member galaxy that you see. And even though Coma ranks among the largest and most massive clusters in the universe, it does not contain enough visible galaxies to account for the observed speeds Zwicky measured. How bad is the situation? Have our known laws of gravity failed us? They certainly work within the solar system. Newton showed that you can derive the unique speed that a planet must have to maintain a stable orbit at any distance from the sun, lest it descend back towards the sun or ascend to a farther orbit. Turns out, if we could boost Earth's orbital speed to more than the square root of 2, 1.4142 times its current value, our planet would achieve escape velocity, and leave the solar system entirely. We can apply the same reasoning to much larger systems, such as our own Milky Way galaxy, in which stars move in orbits that respond to the gravity from all the other stars. Or in clusters of galaxies, where each galaxy likewise feels the gravity from all the other galaxies. In this spirit, amid a page of formulas in his notebook, Einstein wrote a rhyme, more ringingly in German than in this English translation, in honor of Isaac Newton. Look unto the stars to teach us how the master's thoughts can reach us. Each one follows Newton's math, silently along its path. When we examine the Coma cluster, as Zwicky did during the 1930s, we find that its member galaxies are all moving more rapidly than the escape velocity for the cluster. The cluster should swiftly fly apart, leaving barely a trace of its beehive existence after just a few 100 million years had passed. But the cluster is more than 10 billion years old, which is nearly as old as the universe itself. And so was born what remains the longest standing unsolved mystery in astrophysics. Across the decades that followed Zwicky's work, other galaxy clusters revealed the same problem, so Coma could not be blamed for being peculiar. Then what or whose should we blame? Newton? I wouldn't, not just yet. His theories have been examined for 250 years and passed all tests. Einstein? No. The formidable gravity of galaxy clusters is still not high enough to require the full hammer of Einstein's general theory of relativity, just 2 decades old when Zwicky did his research. Perhaps the missing mass needed to bind the Coma cluster's galaxies does exist, but in some unknown invisible form. Today we've settled on the moniker dark matter, which makes no assertion that anything is missing, yet nonetheless implies that some new kind of matter must exist, waiting to be discovered. Just as astrophysicists had come to accept dark matter in galaxy clusters as a mysterious thing, the problem reared its invisible head once again. In 1976, the late Vera Rubin, an astrophysicist at the Carnegie Institution of Washington, discovered a similar mass anomaly within spiral galaxies themselves. Studying the speeds at which stars orbit their galactic centers, Rubin first found what she expected. Within the visible disk of each galaxy, the stars farther from the center move at greater speeds than the stars close in. The farther stars have more matter, stars and gas, between themselves and the galaxy center, enabling their higher orbital speeds. Beyond the galaxy's luminous disk, however, one can still find some isolated gas clouds and a few bright stars. Using these objects as tracers of the gravity field exterior to the most luminous parts of the galaxy, where no more visible matter adds to the total, Rubin discovered that their orbital speeds, which should now be falling with increasing distance out there in Nowheresville, in fact remained high. These largely empty volumes of space, the far rural regions of each galaxy, contain too little visible matter to explain the anomalously high orbital speeds of the tracers. Rubin correctly reasoned that some form of dark matter must lie in these far-out regions, well beyond the visible edge of each spiral galaxy. Thanks to Rubin's work, we now call these mysterious zones dark matter halos. This halo problem exists under our noses, right in the Milky Way, from galaxy to galaxy and from cluster to cluster. The discrepancy between the mass tallied from visible objects and the object's mass estimated from total gravity ranges from a factor of a few up to, in some cases, a factor of many hundreds. Across the universe, the discrepancy averages to a factor of 6. Cosmic dark matter has about 6 times the total gravity of all the visible matter. Further research has revealed that the dark matter cannot consist of ordinary matter that happens to be underluminous or non-luminous. This conclusion rests on 2 lines of reasoning. First, we can eliminate with near certainty all plausible familiar candidates, like the suspects in a police lineup. Could the dark matter reside in black holes? No, we think that we would have detected this many black holes from their gravitational effects on nearby stars. Could it be dark clouds? No, they would absorb or otherwise interact with light from stars behind them, which bona fide dark matter doesn't do. Could it be interstellar or intergalactic rogue planets, asteroids, and comets, all of which produce no light of their own? It's hard to believe that the universe would manufacture 6 times as much mass in planets as in stars. That would mean 6,000 Jupiters for every star in the galaxy, or worse yet, 2 million Earths. In our own solar system, for example, everything that is not the sun adds up to less than 1/5 of 1% of the sun's mass. More direct evidence for the strange nature of dark matter comes from the relative amount of hydrogen and helium in the universe. Together, these numbers provide a cosmic fingerprint left behind by the early universe. To a close approximation, nuclear fusion during the first few minutes after the Big Bang left behind 1 helium nucleus for every 10 hydrogen nuclei, which are themselves simply protons. Calculations show that if most of the dark matter had involved itself in nuclear fusion, there would be much more helium relative to hydrogen in the universe. From this, we conclude that most of the dark matter, hence most of the mass in the universe, does not participate in nuclear fusion, which disqualifies it as ordinary matter, whose essence lies in its willingness to participate in the atomic and nuclear forces that shape matter as we know it. Detailed observations of the cosmic microwave background, which allow a separate test of this conclusion, verify the result. Dark matter and nuclear fusion don't mix. Thus, as best as we can figure, the dark matter doesn't simply consist of matter that happens to be dark. Instead, it's something else altogether. Dark matter exerts gravity according to the same rules that ordinary matter follows, but it does little else that might allow us to detect it. Of course, we are hamstrung in this analysis by not knowing what dark matter is in the first place. If all mass has gravity, does all gravity have mass? We don't know. Maybe there's nothing the matter with the matter, and it's the gravity we don't understand. The discrepancy between dark and ordinary matter varies significantly from one astrophysical environment to another, but it becomes more pronounced for large entities such as galaxies and galaxy clusters. For the smallest objects, such as moons and planets, no discrepancy exists. Earth's surface gravity, for example, can be explained entirely by the stuff that's under our feet. If you're overweight on Earth, don't blame dark matter. Dark matter also has no bearing on the moon's orbit around Earth, nor on the movements of the planets around the sun. But as we've already seen, we do need it to explain the motions of the stars around the center of the galaxy. Does a different kind of gravitational physics operate on the galactic scale? Probably not. More likely, dark matter consists of matter whose nature we have yet to divine, and which gathers more diffusely than ordinary matter does. Otherwise, we would detect the gravity of concentrated chunks of dark matter dotting the universe. Dark matter comets, dark matter planets, dark matter galaxies. As far as we can tell, that's not the way things are. What we know is that the matter we have come to love in the universe, the stuff of stars, planets, and life, is only a light frosting on the cosmic cake, modest buoys afloat in a vast cosmic ocean of something that looks like nothing. During the first 500,000 years after the Big Bang, a mere eye blink in the 14 billion year sweep of cosmic history, matter in the universe had already begun to coalesce into the blobs that would become clusters and superclusters of galaxies. But the cosmos would double in size during its next 500,000 years and continue growing after that. At odds in the universe were two competing effects. Gravity wants to make stuff coagulate, but the expansion wants to dilute it. If you do the math, you rapidly deduce that the gravity from ordinary matter could not win this battle by itself. It needed the help of dark matter, without which we would be living, actually not living, in a universe with no structures, no clusters, no galaxies, no stars, no planets, no people. How much gravity from dark matter did it need? 6 times as much as that provided by ordinary matter itself. Just the amount we measure in the universe. This analysis doesn't tell us what dark matter is, only that dark matter's effects are real, and that, try as you might, you cannot credit ordinary matter for it. So, dark matter is our frenemy. We have no clue what it is. It's kind of annoying, but we desperately need it in our calculations to arrive at an accurate description of the universe. Scientists are generally uncomfortable whenever we must base our calculations on concepts we don't understand. But we'll do it if we have to. And dark matter is not our first rodeo. In the 19th century, for example, scientists measured the energy output of our sun and showed its effect on our seasons and climate long before anyone knew that thermonuclear fusion is responsible for that energy. At the time, the best ideas included the retrospectively laughable suggestion that the sun was a burning lump of coal. Also in the 19th century, we observed stars, obtained their spectra, and classified them long before the 20th century introduction of quantum physics, which gives us our understanding of how and why these spectra look the way they do. Unrelenting skeptics might compare the dark matter of today to the hypothetical, now defunct ether proposed in the 19th century as the weightless, transparent medium permeating the vacuum of space through which light moved. Until a famous 1887 experiment in Cleveland showed otherwise, performed by Albert Michelson and Edward Morley at Case Western Reserve University, scientists asserted that the ether must exist, even though not a shred of evidence supported this presumption. As a wave, light was thought to require a medium through which to propagate its energy, much as sound requires air or some other substance to transmit its waves. But light turns out to be quite happy traveling through the vacuum of space, devoid of any medium to carry it. Unlike sound waves, which consist of air vibrations, light waves were found to be self-propagating packets of energy, requiring no assistance at all. Dark matter ignorance differs fundamentally from ether ignorance. The ether was a placeholder for our incomplete understanding, whereas the existence of dark matter derives not from mere presumption, but from the observed effects of its gravity on visible matter. We're not inventing dark matter out of thin space. Instead, we deduce its existence from observational facts. Dark matter is just as real as the countless exoplanets discovered in orbit around stars other than the sun, discovered solely through their gravitational influence on their host stars, and not from direct measurement of their light. The worst that can happen is we discover that dark matter does not consist of matter at all, but of something else. Could we be seeing the effects of forces from another dimension? Are we feeling the ordinary gravity of ordinary matter crossing the membrane of a phantom universe adjacent to ours? If so, this could be just one of an infinite assortment of universes that comprise the multiverse. Sounds exotic and unbelievable, but is it any more crazy than the first suggestions that Earth orbits the sun? That the sun is one of 100 billion stars in the Milky Way? Or that the Milky Way is but one of 100 billion galaxies in the universe? Even if any of these fantastical accounts prove true, none of it would change the successful invocation of dark matter's gravity in the equations that we use to understand the formation and evolution of the universe. Other unrelenting skeptics might declare that seeing is believing, an approach to life that works well in many endeavors, including mechanical engineering, fishing, and perhaps dating. It's also good, apparently, for residents of Missouri, but it doesn't make for good science. Science is not just about seeing, it's about measuring, preferably with something that's not your own eyes, which are inextricably conjoined with the baggage of your brain. That baggage is more often than not a satchel of preconceived ideas, post-conceived notions, and outright bias. Having resisted attempts to detect it directly on Earth for 3/4 of a century, dark matter remains in play. Particle physicists are confident that dark matter consists of a ghostly class of undiscovered particles that interact with matter via gravity, but otherwise interact with matter or light only weakly or not at all. If you like gambling on physics, this option is a good bet. The world's largest particle accelerators are trying to manufacture dark matter particles amid the detritus of particle collisions. And specially designed laboratories buried deep underground are trying to detect dark matter particles passively in case they wander in from space. An underground location naturally shields the facility from known cosmic particles that might trip the detectors as dark matter imposters. Although it could all be much ado about nothing, The idea of an elusive dark matter particle has good precedence. Neutrinos, for instance, were predicted and eventually discovered, even though they interact extremely weakly with ordinary matter. The copious flux of neutrinos from the Sun, 2 neutrinos for every helium nucleus fused from hydrogen in the Sun's thermonuclear core, exit the Sun unfazed by the Sun itself, travel through the vacuum of space at nearly the speed of light, then pass through Earth as though it does not exist. The tally? Night and day, 100 billion neutrinos from the Sun pass through each thumbnail square patch of your body every second, without a trace of interaction with your body's atoms. In spite of this elusivity, neutrinos are nonetheless stoppable under special circumstances, and if you can stop a particle at all, you've detected it. Dark matter particles may reveal themselves through similarly rare interactions, or more amazingly, they might manifest via forces other than the strong nuclear force, weak nuclear force, and electromagnetism. These 3 plus gravity complete the Fab 4 forces of the universe, mediating all interactions between and among all known particles. So the choices are clear. Either dark matter particles must wait for us to discover and control a new force or class of forces through which their particles interact, or else dark matter particles interact via normal forces, but with staggering weakness. So, dark matter's effects are real. We just don't know what it is. Dark matter seems not to interact through the strong nuclear force, so it cannot make nuclei. It hasn't been found to interact through the weak nuclear force, something even elusive neutrinos do. It doesn't seem to interact with the electromagnetic force, so it doesn't make molecules and concentrate into dense balls of dark matter. Nor does it absorb or emit or reflect or scatter light. As we've known from the beginning, dark matter does indeed exert gravity, to which ordinary matter responds, but that's it. After all these years, we haven't discovered it doing anything else. For now, we must remain content to carry dark matter along as a strange, invisible friend, invoking it where and when the universe requires it of us. Chapter 6. Dark Energy. As if you didn't have enough to worry about, the universe in recent decades was discovered to wield a mysterious pressure that issues forth from the vacuum of space, and that acts opposite cosmic gravity. Not only that, this negative gravity will ultimately win the tug of war as it forces the cosmic expansion to accelerate exponentially into the future. For the most mind-warping ideas of 20th century physics, just blame Einstein. Albert Einstein hardly ever set foot in the laboratory. He didn't test phenomena or use elaborate equipment. He was a theorist who perfected the thought experiment, in which you engage nature through your imagination by inventing a situation or model and then working out the consequences of some physical principle. In Germany, before World War II, laboratory-based physics far outranked theoretical physics in the minds of most Aryan scientists. Jewish physicists were all relegated to the lowly theorist's sandbox and left to fend for themselves. And what a sandbox that would become. As was the case for Einstein, if a physicist model intends to represent the entire universe, then manipulating the model should be tantamount to manipulating the universe itself. Observers and experimentalists can then go out and look for the phenomenon predicted by that model. If the model is flawed, or if the theorists make a mistake in their calculations, the observers will uncover a mismatch between the model's predictions and the way things happen in the real universe. That's the first cue for a theorist to return to the proverbial drawing board by either adjusting the old model or creating a new one. One of the most powerful and far-reaching theoretical models ever devised, already introduced in these pages, is Einstein's general theory of relativity. But you can call it GR after you get to know it better. Published in 1916, GR outlines the relevant mathematical details of how everything in the universe moves under the influence of gravity. Every few years, lab scientists devise ever more precise experiments to test the theory, only to further extend the envelope of the theory's accuracy. A modern example of this stunning knowledge of nature that Einstein has gifted us comes from 2016, when gravitational waves were discovered by a specially designed observatory tuned for just this purpose. These waves, predicted by Einstein, are ripples moving at the speed of light across the fabric of spacetime and are generated by severe gravitational disturbances such as the collision of two black holes. And that's exactly what was observed. The gravitational waves of the first detection were generated by a collision of black holes in a galaxy 1.3 billion light years away, and at a time when Earth was teeming with simple single-celled organisms. While the ripple moved through space in all directions, Earth would, after another 800 million years, evolve complex life, including flowers and dinosaurs and flying creatures, as well as a branch of vertebrates called mammals. Among the mammals, a sub-branch would evolve frontal lobes and complex thought to accompany them. We call those primates. A single branch of these primates would develop a genetic mutation that allowed speech, and that branch, Homo sapiens, would invent agriculture, civilization, and philosophy, and art and science, all in the last 10,000 years. Ultimately, one of its 20th century scientists would invent relativity out of his head and predict the existence of gravitational waves. A century later, technology capable of seeing these waves would finally catch up with the prediction, just days before that gravity wave, which had been traveling for 1.3 billion years, washed over Earth and was detected. Yes, Einstein was a badass. When first proposed, most scientific models are only half-baked, leaving wiggle room to adjust parameters for a better fit to the known universe. In the sun-based heliocentric universe, conceived by the 16th century mathematician Nicholas Copernicus, planets orbited in perfect circles. The orbit the sun part was correct and a major advance in the Earth-based geocentric universe, but the perfect circle part turned out to be a bit off. All planets orbit the sun in flattened circles, called ellipses, and even that shape is just an approximation of a more complex trajectory. Copernicus's basic idea was correct, and that's what mattered most. It simply required some tweaking to make it more accurate. Yet, in the case of Einstein's relativity, the founding principles of the entire theory require that everything must happen exactly as predicted. Einstein had, in effect, built what looks on the outside like a house of cards, with only 2 or 3 simple postulates holding up the entire structure. Indeed, upon learning of a 1931 book entitled 100 Authors Against Einstein, he responded that if he were wrong, then only one would have been enough. Therein were sown the seeds of one of the most fascinating blunders in the history of science. Einstein's new equations of gravity included a term he called the cosmological constant, which he represented by the capital Greek letter lambda. A mathematically permitted but optional term, the cosmological constant allowed him to represent a static universe. Back then, the idea that our universe would be doing anything at all other than simply existing was beyond anyone's imagination. So lambda's sole job was to oppose gravity within Einstein's model, keeping the universe in balance, resisting the natural tendency for gravity to pull the whole universe into one giant mass. Einstein invented a universe that neither expands nor contracts, consistent with everybody's expectations at the time. The Russian physicist Alexander Friedmann would subsequently show mathematically that Einstein's universe, though balanced, was in an unstable state, like a ball resting on the top of a hill, awaiting the slightest provocation to roll down in one direction or another, or like a pencil balanced on its sharpened point. Einstein's universe was precariously perched between a state of expansion and total collapse. Moreover, Einstein's theory was new, and just because you give something a name does not make it real. Einstein knew that lambda, as a negative gravity force of nature, had no known counterpart in the physical universe. Einstein's general theory of relativity radically departed from all previous thinking about gravitational attraction. Instead of settling for Sir Isaac Newton's view of gravity as spooky action at a distance, a conclusion that made Newton himself uncomfortable, GR regards gravity as the response of a mass to the local curvature of space and time, caused by some other mass or field of energy. In other words, concentrations of mass cause distortions, dimples really, in the fabric of space and time. These distortions guide the moving masses along straight-line geodesics, the shortest distance between 2 points on the surface, though they look to us like the curved trajectories we call orbits. The 20th century American theoretical physicist John Archibald Wheeler said it best, summing up Einstein's concept as, matter tells space how to curve, space tells matter how to move. At the end of the day, general relativity described 2 kinds of gravity. One is the familiar kind, like the attraction between Earth and a ball thrown into the air, or between the sun and the planets. It also predicted another variety, a mysterious anti-gravity pressure associated with the vacuum of space-time itself. Lambda preserved what Einstein and every other physicist of his day had strongly presumed to be true: the status quo of a static universe. An unstable static universe. To invoke an unstable condition as the natural state of a physical system violates scientific credo. You cannot assert that the entire universe is a special case that happens to be balanced forever and ever. Nothing ever seen, measured, or imagined has behaved this way in the history of science, which makes for powerful precedent. 13 years later, in 1929, the American astrophysicist Edwin P. Hubble discovered that the universe is not static. He had found and assembled convincing evidence that the more distant a galaxy, the faster the galaxy recedes from the Milky Way. In other words, the universe is expanding. Now, embarrassed by the cosmological constant, which corresponded to no known force of nature, and by the lost opportunity to have predicted the expanding universe himself, Einstein discarded lambda entirely, calling it his life's greatest blunder. By yanking lambda from the equation, he presumed its value to be 0, such as in this example. Assume A equals B plus C. If you learn later that A equals 10 and B equals 10, then A still equals B plus C, except in that case C equals 0, and it's rendered unnecessary in the equation. But that wasn't the end of the story. Off and on over the decades, theorists would extract lambda from the crypt, imagining what their ideas would look like in a universe that had a cosmological constant. 69 years later, in 1998, science exhumed lambda one last time. Early that year, remarkable announcements were made by 2 competing teams of astrophysicists, one led by Saul Perlmutter of Lawrence Berkeley National Laboratory in Berkeley, California, and the other co-led by Brian Schmidt of Mount Stromlo and Siding Spring Observatories in Canberra, Australia, and Adam Rees of the Johns Hopkins University in Baltimore, Maryland. Dozens of the most distant supernovas ever observed appeared noticeably dimmer than expected, given the well-documented behavior of this species of exploding star. Reconciliation required that either those distant supernovas behaved unlike their nearer brethren, or they were as much as 15% farther away than where the prevailing cosmological models had placed them. The only known thing that naturally accounts for this acceleration is Einstein's lambda, the cosmological constant. When astrophysicists dusted it off and put it back into Einstein's original equations for general relativity, the known state of the universe matched the state of Einstein's equations. The supernovas used in Perlmutter's and Schmidt's studies are worth their weight in fusionable nuclei. Within certain limits, each of those stars explodes the same way, igniting the same amount of fuel, releasing the same titanic amount of energy in the same amount of time, thereby reaching the same peak luminosity. Thus, they serve as a kind of yardstick or standard candle for calculating cosmic distances to the galaxies in which they explode, out to the farthest reaches of the universe. Standard candles simplify calculations immensely. Since the supernovas all have the same wattage, the dim ones are far away and the bright ones are close by. After measuring their brightness, a simple task, you can tell exactly how far they are from you and from one another. If the luminosities of the supernovas were all different, you could not use brightness alone to tell how far away one was in comparison with another. A dim one could be either a high wattage bulb far away or a low wattage bulb close up. All fine, but there's a second way to measure the distance to the galaxies, their speed of recession from the Milky Way. Recession that's part and parcel of the overall cosmic expansion. As Hubble was the first to show, the expanding universe makes distant objects race away from us faster than nearby ones. So, by measuring a galaxy's speed of recession, another simple task, one can deduce a galaxy's distance. If those two well-tested methods give different distances for the same object, something must be wrong. Either the supernovas are bad standard candles, or a model for the rate of cosmic expansion as measured by galaxy speeds is wrong. Well, something was wrong. It turned out that the supernovas were splendid standard candles, surviving the careful scrutiny of many skeptical investigators. And so astrophysicists were left with a universe that had expanded faster than we thought, placing galaxies farther away than their recession speed would have otherwise indicated. And there was no easy way to explain the extra expansion without invoking lambda, Einstein's cosmological constant. Here was the first direct evidence that a repulsive force permeated the universe, opposing gravity, which is how and why the cosmological constant rose from the dead. Lambda suddenly acquired a physical reality that needed a name, and so dark energy took center stage in cosmic drama, suitably capturing both the mystery and our associated ignorance of its cause. Perlmutter, Schmidt, and Rees justifiably shared the 2011 Nobel Prize in Physics for this discovery. The most accurate measurements to date reveal dark energy as the most prominent thing in town, currently responsible for 68% of all the mass energy in the universe. Dark matter comprises 27%, with regular matter comprising a mere 5%. The shape of our four-dimensional universe comes from the relationship between the amount of matter and energy that lives in the cosmos and the rate at which the cosmos is expanding. A convenient mathematical measure of this is omega, yet another capital Greek letter with a firm grip on the cosmos. If you take the matter-energy density of the universe and divide it by the matter-energy density required to just barely halt the expansion, known as the critical density, you get omega. Since both mass and energy cause space-time to warp, curve, omega tells us the shape of the cosmos. If omega is less than 1, the actual mass energy falls below the critical value, and the universe expands forever in every direction for all of time, taking on the shape of a saddle in which initially parallel lines diverge. If omega equals 1, the universe expands forever, but only barely so. In that case, the shape is flat, preserving all the geometric rules we learned in high school about parallel lines. If omega exceeds 1, parallel lines converge and the universe curves back on itself, ultimately recollapsing into the fireball whence it came. At no time since Hubble discovered the expanding universe has any team of observers ever reliably measured omega to be anywhere close to 1. Adding up all the mass and energy their telescopes could see, and even extrapolating beyond these limits, dark matter included, the biggest values from the best observations topped out at about omega equals 0.3. As far as observers were concerned, the universe was open for business, riding a one-way saddle into the future. Meanwhile, beginning in 1979, the American physicist Alan H. Guth of the Massachusetts Institute of Technology and others advanced an adjustment to the Big Bang theory that cleared up some nagging problems with getting a universe to be as smoothly filled with matter and energy as ours is known to be. A fundamental byproduct of this update to the Big Bang was that it drives omega toward 1, not toward a half, not toward 2, not toward a million, toward 1. Hardly a theorist in the world had a problem with that requirement, because it helped get the Big Bang to account for the global properties of the known universe. There was, however, another little problem. The update predicted 3 times as much mass energy as observers could find. Undeterred, the theorists said the observers just weren't looking hard enough. At the end of the tallies, visible matter alone could account for no more than 5% of the critical density.
All about the
How about the mysterious dark matter? They added that too. Nobody knew what it was, and we still don't know what it is, but surely it contributed to the totals. From there, we get 5 or 6 times as much dark matter as visible matter. But that's still way too little. Observers were at a loss, and the theorists answered, keep looking. Both camps were sure the other was wrong, until the discovery of dark energy. That single component, when added to the ordinary matter and the ordinary energy and dark matter, raised the mass energy density of the universe to the critical level, simultaneously satisfying both the observers and the theorists. For the first time, the theorists and observers kissed and made up. Both, in their own way, were correct. Omega does equal 1, just as the theorists demanded of the universe, even though you can't get there by adding up all the matter, dark or otherwise, as they had naively presumed. There's no more matter running around the cosmos today than had ever been estimated by the observers. Nobody had foreseen the dominating presence of cosmic dark energy, nor had anybody imagined it as the great reconciler of differences. So what is this stuff? Nobody knows. The closest anybody has come is to presume dark energy is a quantum effect, where the vacuum of space, instead of being empty, actually seethes with particles and their antimatter counterparts. They pop in and out of existence in pairs and don't last long enough to be measured. Their transient existence is captured in their moniker, virtual particles. The remarkable legacy of quantum physics, the science of the small, demands that we give this idea serious attention. Each pair of virtual particles exerts a little bit of outward pressure as it ever so briefly elbows its way into space. Unfortunately, when you estimate the amount of repulsive vacuum pressure that rises from the abbreviated lives of virtual particles, the result is more than 10 to the power 120 times larger than the experimentally determined value of the cosmological constant. This is a stupidly large factor, leading to the biggest mismatch between theory and observation in the history of science. Yes, we're clueless, but it's not abject cluelessness. Dark energy is not adrift with nary a theory to anchor it. Dark energy inhabits one of the safest harbors we can imagine, Einstein's equations of general relativity. It's the cosmological constant. It's lambda. Whatever dark energy turns out to be, we already know how to measure it and how to calculate its effects on the past, present, and future of the cosmos. Without a doubt, Einstein's greatest blunder was having declared that lambda was his greatest blunder. And the hunt is on. Now that we know dark energy is real, teams of astrophysicists have begun ambitious programs to measure distances and the growth of structure in the universe using ground-based and spaceborne telescopes. These observations will test the detailed influence of dark energy on the expansion history of the universe, and will surely keep theorists busy. They desperately need to atone for how embarrassing their calculation of dark energy turned out to be. Do we need an alternative to GR? Does the marriage of GR and quantum mechanics require an overhaul? Or is there some theory of dark energy that awaits discovery by a clever person yet to be born? A remarkable feature of lambda in the accelerating universe is that the repulsive force arises from within the vacuum, not from anything material. As the vacuum grows, the density of matter and familiar energy within the universe diminishes, and the greater becomes lambda's relative influence on the cosmic state of affairs. With greater repulsive pressure comes more vacuum, and with more vacuum comes greater repulsive pressure, forcing an endless and exponential acceleration of the cosmic expansion. As a consequence, anything not gravitationally bound to the neighborhood of the Milky Way galaxy will recede at ever-increasing speed as part of the accelerating expansion of the fabric of space-time. Distant galaxies, now visible in the night sky, will ultimately disappear beyond an unreachable horizon, receding from us faster than the speed of light, a feat allowed not because they're moving through space at such speeds, but because the fabric of the universe itself carries them at such speeds. No law of physics prevents this. In 1 trillion or so years, anyone alive in our own galaxy may know nothing of other galaxies. our observable universe will merely comprise a system of nearby long-lived stars within the Milky Way, and beyond this starry night will lie an endless void. Darkness in the face of the deep. Dark energy, a fundamental property of the cosmos, will, in the end, undermine the ability of future generations to comprehend the universe they've been dealt. Unless contemporary astrophysicists across the galaxy keep remarkable records and bury an awesome trillion-year time capsule, post-apocalyptic scientists will know nothing of galaxies, the principal form of organization for matter in our cosmos, and will thus be denied access to key pages from the cosmic drama that is our universe. Behold my recurring nightmare. Are we too missing some basic pieces of the universe that once were? What part of the cosmic history book has been marked access denied? What remains absent from our theories and equations that ought to be there, leaving us groping for answers we may never find? Chapter 7. The Cosmos on the Table. Trivial questions sometimes require deep and expansive knowledge of the cosmos just to answer them. In middle school chemistry class, I asked my teacher where the elements on the periodic table came from. He replied, Earth's crust. I'll grant him that. It's surely where the supply lab gets them, but how did Earth's crust acquire them? The answer must be astronomical. But in this case, do you actually need to know the origin and evolution of the universe to answer the question? Yes, you do. Only 3 of the naturally occurring elements were manufactured in the Big Bang. The rest were forged in the high-temperature hearts and explosive remains of dying stars, enabling subsequent generations of star systems to incorporate this enrichment, forming planets, and in our case, people. For many, the periodic table of chemical elements is a forgotten oddity, a chart of boxes filled with mysterious cryptic letters last encountered on the wall of high school chemistry class. As the organizing principle for the chemical behavior of all known and yet to be discovered elements in the universe, the table instead ought to be a cultural icon, a testimony to the enterprise of science as an international human adventure conducted in laboratories, particle accelerators, and on the frontier of the cosmos itself. Yet every now and then, even a scientist can't help thinking of the periodic table as a zoo of one-of-a-kind animals conceived by Dr. Seuss. How else could we believe that sodium is a poisonous reactive metal that you can cut with a butter knife, while pure chlorine is a smelly, deadly gas, yet when added together, they make sodium chloride, a harmless, biologically essential compound better known as table salt? Or how about hydrogen and oxygen? One is an explosive gas and the other promotes violent combustion, yet the two combined make liquid water, which puts out fires. Amid these chemical confabulations, we find elements significant to the cosmos, allowing me to offer the periodic table as viewed through the lens of an astrophysicist. With only one proton in its nucleus, hydrogen is the lightest and simplest element, made entirely during the Big Bang. Out of the 94 naturally occurring elements, hydrogen lays claim to more than 2/3 of all the atoms in the human body, and more than 90% of all atoms in the cosmos, on all scales, right on down to the solar system. Hydrogen in the core of the massive planet Jupiter is under so much pressure that it behaves more like a conductive metal than a gas, creating the strongest magnetic field among the planets. The English chemist Henry Cavendish discovered hydrogen in 1766 during his experiments with H2O. Hydrogenesis is Greek for water forming, but he's best known among astrophysicists as the first to calculate Earth's mass after having measured an accurate value for big G, the gravitational constant in Newton's famous equation. Every second of every day, 4.5 billion tons of fast-moving hydrogen nuclei are turned into energy as they slam together to make helium within the 15 million degree core of the sun. Helium is widely recognized as an over-the-counter low-density gas that, when inhaled, temporarily increases the vibrational frequency of your windpipe and larynx, making you sound like Mickey Mouse. Helium is the second simplest and second most abundant element in the universe. Although a distant second to hydrogen in abundance, there's 4 times more of it than all other elements in the universe combined. One of the pillars of Big Bang cosmology is the prediction that in every region of the cosmos, no less than about 10% of all atoms are helium, manufactured in that percentage across the well-mixed primeval fireball that was the birth of our universe. Since the thermonuclear fusion of hydrogen within stars gives you helium, some regions of the cosmos could easily accumulate more than their 10% share of the stuff. But as predicted, no one has ever found a region of the galaxy with less. Some 30 years before it was discovered and isolated on Earth, astronomers detected helium in the spectrum of the sun's corona during the total eclipse of 1868. As noted earlier, the name helium was duly derived from Helios, the Greek sun god, and with 92% of hydrogen's buoyancy in air, but without its explosive characteristics, helium is the gas of choice for the outsized balloon characters of the Macy's Thanksgiving Day Parade, making the department store second only to the U.S. military as the nation's top user of the element. Lithium is the third simplest element in the universe, with 3 protons in its nucleus. Like hydrogen and helium, lithium was made in the Big Bang. But unlike helium, which can be manufactured in stellar cores, lithium is destroyed by every known nuclear reaction. Another prediction of Big Bang cosmology is that we can expect no more than 1% of the atoms in any region of the universe to be lithium. No one has yet found a galaxy with more lithium than this upper limit supplied by the Big Bang. The combination of helium's upper limit and lithium's lower limit gives us a potent dual constraint on tests for Big Bang cosmology. The element carbon can be found in more kinds of molecules than the sum of all other kinds of molecules combined. Given the abundance of carbon in the cosmos, forged in the cores of stars, churned up to their surfaces, and released copiously into the galaxy, a better element does not exist on which to base the chemistry and diversity of life. Just edging out carbon in abundance rank, oxygen is common too, forged and released in the remains of exploded stars. Both oxygen and carbon are major ingredients of life as we know it. But what about life as we don't know it? How about life based on the element silicon? Silicon sits directly below carbon on the periodic table, which means, in principle, it can create the same portfolio of molecules that carbon does. And yet, we expect carbon to win because it's 10 times more abundant than silicon in the cosmos. But that doesn't stop science fiction writers who keep exobiologists on their toes, wondering what the first truly alien silicon-based life forms will be like. In addition to being an active ingredient in table salt, sodium is the most common glowing gas in municipal street lamps across the nation. They burn brighter and longer than incandescent bulbs, although they may all soon be replaced by LEDs, which are even brighter at a given wattage and cheaper. 2 varieties of sodium lamps are common: high-pressure lamps, which look yellow-white, and the rarer low-pressure lamps, which look orange. Turns out, while all light pollution is bad for astrophysics, the low-pressure sodium lamps are least bad because their contamination can be easily subtracted from telescope data. In a model of cooperation, the entire city of Tucson, Arizona, the nearest large municipality to the Kitt Peak National Observatory, has, by agreement with the local astrophysicists, converted all its streetlights to low-pressure sodium lamps. Aluminum occupies nearly 10% of Earth's crust, yet was unknown to the ancients and unfamiliar to our great-grandparents. The element was not isolated and identified until 1827, and did not enter common household use until the late 1960s, when tin cans and tinfoil yielded to aluminum cans and, of course, aluminum foil. I bet most old people you know still call it tin foil. Polished aluminum makes a near-perfect reflector of visible light and is the coating of choice for nearly all telescope mirrors today. Titanium is 1.7 times denser than aluminum, but it's more than twice as strong. So titanium, the ninth most abundant element in Earth's crust, has become a modern darling for many applications, such as military aircraft components and prosthetics that require a light, strong metal for their tasks. In most cosmic places, the number of oxygen atoms exceeds that of carbon. After every carbon atom has latched onto the available oxygen atoms, forming carbon monoxide or carbon dioxide, the leftover oxygen bonds with other things like titanium. The spectra of red stars are riddled with features traceable to titanium oxide, which itself is no stranger to stars on Earth. Star sapphires and rubies owe their radiant asterisms to titanium oxide impurities in their crystal lattice. Furthermore, the white paint used for telescope domes features titanium oxide, which happens to be highly reflective in the infrared part of the spectrum, greatly reducing the heat accumulated from sunlight in the air surrounding the telescope. At nightfall, with the dome open, the air temperature near the telescope rapidly equals the temperature of the nighttime air, allowing light from stars and other cosmic objects to be sharp and clear. And while not directly named for a cosmic object, titanium derives from the Titans of Greek mythology. Titan is Saturn's largest moon. By many measures, iron ranks as the most important element in the universe. Massive stars manufacture elements in their core, in sequence from helium to carbon to oxygen to nitrogen and so forth, all the way up the periodic table to iron. With 26 protons and at least as many neutrons in its nucleus, iron's odd distinction comes from having the least total energy per nuclear particle of any element. This means something quite simple. If you split iron atoms via fission, they will absorb energy. And if you combine iron atoms via fusion, they will also absorb energy. Stars, however, are in the business of making energy. As high-mass stars manufacture and accumulate iron in their cores, they are nearing death. Without a fertile source of energy, the star collapses under its own weight and instantly rebounds in a stupendous supernova explosion, outshining 1 billion suns for more than a week. The soft metal gallium has such a low melting point that, like cocoa butter, it will liquefy on contact with your hand. Apart from this parlor demo, gallium is not interesting to astrophysicists except as one of the ingredients in the gallium chloride experiments used to detect elusive neutrinos from the sun. A huge 100-ton underground vat of liquid gallium chloride is monitored for any collisions between neutrinos and gallium nuclei, turning it into germanium. The encounter emits a spark of X-ray light that is measured every time a nucleus gets slammed. The long-standing solar neutrino problem, with fewer neutrinos were detected than predicted by solar theory, was solved using telescopes such as this. Every form of the element technetium is radioactive. Not surprisingly, it's found nowhere on Earth except in particle accelerators, where we make it on demand. Technetium carries this distinction in its name, which derives from the Greek teknetos, meaning artificial. For reasons not fully understood, technetium lives in the atmospheres of a select subset of red stars. This alone would not be cause for alarm, except that technetium has a half-life of a mere 2 million years, which is much, much shorter than the age and life expectancy of the stars in which it's found. In other words, the star cannot have been born with the stuff, for if it were, there would be none left by now. There is also no known mechanism to create technetium in a star's core and have it dredge itself up to the surface where it is observed, which has led to exotic theories that have yet to achieve consensus in the astrophysics community. Along with osmium and platinum, iridium is one of the 3 heaviest, densest elements on the table. 2 cubic feet of it weighs as much as a Buick, which makes iridium one of the world's best paperweights, able to defy all known office fans. Iridium is also the world's most famous smoking gun. A thin layer of it can be found worldwide at the famous Cretaceous-Paleogene boundary. formerly known as the KT boundary in geologic strata, dating from 65 million years ago. Not so coincidentally, that's when every land species larger than a carry-on suitcase went extinct, including the legendary dinosaurs. Iridium is rare on Earth's surface, but relatively common in 6-mile metallic asteroids, which upon colliding with Earth, vaporized on impact, scattering their atoms across Earth's surface. So whatever might have been your favorite theory for offing the dinosaurs, a killer asteroid the size of Mount Everest from outer space should be at the top of your list. I don't know how Albert would have felt about this, but an unknown element was discovered in the debris of the first hydrogen bomb test in the Eniwetok Atoll in the South Pacific on November 1st, 1952, and was named Einsteinium in his honor. I might have named it Armageddon instead. Meanwhile, 10 entries in the periodic table get their names from objects that orbit the sun. Phosphorus comes